let's actually work one of your homework problems, but one of the ones with a dependent source, because I don't think we've done one of those just yet, and that might be of use to you guys. So I'm going to open up Dropbox 223. Homework. Let's do 7. Blah, blah, blah. Let's look at this guy. Oh, actually, I don't. What's up, Connor?
When might you be?
Oh, have I not posted it yet?
Oh, you may have.
If I haven't posted it, I apologize. I can do that today. It's been written. I handed it to you.
Oh, you got to take.
Yeah, that's it. That's exactly it. Yeah. But for those of you who have been attending class virtually, if I haven't uploaded it, then you haven't gotten a copy of it. So I need to get off my butt and do that. So either way, send me a reminder email to at least check on that, please. Let's copy that. And let's paste this guy in here. All right, so this is going to be our circuit of interest. This is homework 7, problem something. Don't particularly remember or care. So I believe I asked you to solve for the current IA as a function of time. So there are a couple of different ways that we can go about doing that. In my opinion, there are 2 ways that we can do it. One of which is slightly more difficult than the next, okay? So let's talk about the more difficult means by which we can solve this, okay? So during the transient condition for this circuit, with our switch being open, if we were to apply Kirchhoff's current law at the top node of the capacitor, which I will label here, so I'm talking about this node in particular, we could find that the current IA of t plus the current IC of t plus the current IL of t all have to sum together to make 0, which means we could express IA of t as negative IC of t minus IL of t. That is one way for us to determine that quantity, okay? That is what I would consider the more difficult way to do it, okay? The easier way to do it is to recognize that the 7 ohm resistor in series with the 3 IA voltage source in series with the 2 ohm resistor has an equivalent resistance from the perspective of our energy storage elements. It's just a Thevenin resistance looking in from here. And so if we knew the voltage V of t divided by that equivalent resistance will give us IA of t. Both of the methods will get us the answer, but in my opinion, one is significantly easier than the other, and I like to be lazy and do things the easy way. So that's the method that I'm going to suggest you. Nothing stopping you from applying the KCL method, but I'm going to not do that. All right, so our first crap, did not want to erase everything. All right, I'm just going to leave that circle there because I'm afraid if I erase again, it's going to go away. So we're stuck with that now. All right, so the first thing that we need to do is to determine what kind of circuit this is. So the inductor being in parallel with the capacitor gives us a pretty dang strong hint that this is a parallel RLC circuit. agreeing that we can view this left-hand resistive path as a resistor that would be connected in parallel with our capacitor and inductor, then formally says that this is a parallel RLC circuit. For a parallel RLC circuit, alpha is equal to 1 over twice RC, but we have to do some work here to figure out what that R is, okay? So what I'm doing here is I'm going to look at my dead network during the transient condition. So that means my 9-volt source is supposed to be off. My switch is open. Here's my 2 ohm resistor, which is going to carry a current IA. Here's my dependent voltage source, which has a voltage of 3 IA. Here's my 7 ohm resistor. And then these are the terminals that I'm looking in through. So what I'm doing here, I want to be very specific about this, is I'm taking my energy storage elements, plural, out and looking in through the open circuited terminals where they were connected to see the equivalent resistance seen by my energy storage elements. Is that clear? So I'm taking out both my capacitor and my inductor. If this were a series RLC circuit, much like the homework problem from set 8, you can take out the inductor in series with the capacitor and again look in through the terminals left behind by the energy storage elements, okay? So because this network contains a dependent source with no independent sources, I have to utilize a test source method in order to solve for this equivalent resistance. So that means I can connect either a test voltage source or a test current source. Either one will work, but in this particular case, one of them makes it slightly easier than the other. Which one do you guys want to do? Pardon? Current. So the current to me is the one that makes it slightly easier, because if we connect, let's say, a 1 amp current source here, so here's our test source. Here's the V test that we're trying to find. Well, we now know that IA is exactly 1 amp, which makes this fairly trivial to solve for, right? So we could say that V test is equal to 7 ohms times 1 amp, and I need to make that look more like a 7 and less like a 2, minus 3 times 1 amp plus 2 ohms times 1 amp is 6 volts. And from this, our equivalent resistance, RTH, is 6 volts over 1 amp is equal to 6 ohms. How do we feel about applying the test source method to determine the equivalent resistance of a network containing a dependent source? Supposed to be a review from circuits 1. All right. So now we know what our equivalent resistance is. C is obviously 25 millifarads. L, whenever we need it, is obviously 4.444 henries. We can calculate alpha and omega naught, right? So alpha, 1 over twice R Thevenin times C, is going to look like 1 over 2 times 6 ohms. Let's see, 25 millifarads. I don't want to attempt to do that in my head. So 1 over 12 times 25 times 10 to the minus 3. I get 10/3 of a nepper. Omega naught is the square root of 1 over LC. That's the square root of 1 over 25 millifarads. And let's see, 4.444 Henry. Which comes out to be 3.000. I'm going to call it 3 radians per second. It's actually supposed to be 3, but I can't put in fractions in the program that I used to draw these circuits, which is why I had to put it as 4.444, as opposed to whatever fraction that would be that would make this come out to be exactly 3. Anywho. All right, so which is larger? Alpha. So since alpha, yes. Thank you. Nepper per second, absolutely right. Thank you. So since alpha is larger, this is an example of an overdamped circuit, right? Since it's overdamped, before we forget about it, let's go ahead and calculate S1 and S2. S1 is always negative alpha plus the square root of alpha squared minus omega naught squared. So that is negative 10/3 plus the square root of 10/3 squared minus 9. Negative 1.880 per second. And just as a note, I'm storing this in my calculator as variable X. I lied. I'm going to store it as A because if I store it as X, I can't use it in my system solver later. And I'm trying to be as lazy / efficient as possible. All right, so S2 is negative alpha minus the square root of alpha squared minus omega naught squared. Which I get to be negative 4.786 per second, which I'm going to store as variable B. Okay. So we know how the system behaves in as much as it is an overdamped parallel RLC circuit. Now we have to analyze at t is equal to 0 minus, t is equal to 0 plus, and t is equal to infinity. So just as a reminder here, what are the quantities that we're going to have to actually take into account? Now in your homework problem, I think I make you solve for V, I, and probably this I as well. I am just going to solve for what's needed, okay? We're using the capacitor voltage, which means I'm going to need to keep track of the quantity V of t and the current IC of t, and that's it. Everything else is extemporaneous information. At 0 minus, though, I am going to have to keep track of IL of t so that I know how it behaves at t is equal to 0 plus. All right, excuse me. So, yes, sir.
What are your those two parameters. Why is the current through the capacitor significant?
Okay, fantastic question. So the current through the capacitor is significant because I'm going to have a system of equations that involves the voltage drop over the capacitor and the derivative-based relationship, which is the current flowing through the capacitor. So that's why I need to know what the capacitor current is specifically at t is equal to 0 plus. Actually, at all other points in time, it's completely useless. But at t is equal to 0 plus, I need to know what IC of t is in order to set up my system, which tells me what my coefficients of my response is. All right, so I just copied this down again so that I could look at it. I'm going to draw my circuit now at t is equal to 0 minus. So at 0 minus, we're going to have a 9-volt source connected to 2-ohm resistor. We have 3 IA at 0 minus, where here is IA at 0 minus. Here's a 7-ohm resistor. Here is the open circuit, which is playing the role of my capacitor at DC steady state. Here is my short circuit playing the role of my inductor at DC steady state. So this represents V of 0 minus. This is IL of 0 minus. And just for the sake of argument, here's IC at 0 minus. Okay. So which of these quantities can we determine by inspection? IC of 0 minus. Has to be 0 amps. Okay. So V of 0 minus will be 0 volts because it represents the voltage drop over a short circuit, which is inherently 0. So that's also correct. So the only thing that we don't know that we need to know then is the value of the inductor current at t is equal to 0 minus. So what do you want to do? How do you want to solve for that quantity? For this one, no, not necessarily. So we could, I don't particularly want to, but we could just simply do mesh here, right? We have an obvious mesh on the left-hand side and then a larger mesh on the right-hand side. The reason why I say I don't want to is because I feel strongly that it's unnecessary. We can see, I believe, by inspection, that the quantity IA, the current flowing down through the 2-ohm resistor, is 4.5 amps because the 2-ohm resistor is in parallel with a 9-volt source. Which means we can do KVL around the outside loop and figure out what I is with a single equation, which is how I would prefer to do it. So I'm saying negative 9 volts plus 3 times IA, where IA is a known quantity, plus 7 IL has to equal 0, and then we solve for IL.
Could you do source transformation?
No. The reason why I say no is because the voltage drop across this source, the dependent source, depends on IA. And as soon as we do a source transformation, IA is gone.
Okay.
Right? Because IA is the current flowing through this 2-ohm resistor when it's here, not when it's somewhere else.
Thank you. How do you do it? Iron with 4.5?
A 9-volt source is in parallel with a 2 ohm resistor. So Ohm's law tells us that
Oh,
the current flowing through it is 9/2. Is that reasonable?
yeah.
Yeah. Okay. All right. So -9 volts plus 3 times 4.5 amps plus 7 ohms times IL at 0 minus is equal to 0 tells us that IL at 0 minus is 9 plus 13.5 divided by 7, if my algebra is correct. That's not correct. Sorry. Because it should be 9 minus 13.5. Which is -4.5/7. Yes. Oh, you doing the work, I don't care how you do it. Yeah. I just don't want to set up a system of equations, so I thought of a way to not set up a system. Yeah, if you want to default to mesh, that's great. I'm going to try to give you circuits where that will mess with you because I'm a jerk, but hey, I've told you about it, so at least you're aware. All right, so since I made a dumb mistake here with the sign, let's make sure we're correct here. So I'm moving the 9 volts to the right-hand side. I'm moving the 3 times 4.5, which is 13.5 over, so that's 9 minus 13.5, and then I divide by the 7 ohm path right here. So that seems correct to me. Let's make this a little bit nicer and call this -9/14, so that we don't have decimals in our fractions. Catherine, did I screw anything up? Mhm. Kirchhoff's voltage law around the outside loop. So -9 volts plus 3 IA plus 7 times this current that we're looking for. And then I'm back at the bottom node. So I'm done. So they equal 0. Nope. Because I'm specifically doing it around the outside loop. Absolutely. I can choose any path. Yeah. So if we were doing it as mesh, we'd do this guy, an equation for this guy, and an equation for this guy, right? And then solve those two equations. Well, if this loop is equal to 0, and this loop is equal to 0, and 0 plus 0 is equal to 0, I can go around the outside loop, no problem. So when I'm applying Kirchhoff's voltage law, as long as I start and end at the same node, it doesn't matter what loop I choose. So any of the 3 loops here can have a KVL equation written. The one I chose was specific such that I would get the quantity IL as my only unknown. Okay. All right, so -9/14 amps goes. Okay, so do we feel comfortable enough about our analysis at t is equal to 0 minus to move on to t is equal to 0 plus? Okay. So at t is equal to 0 plus, our switch has opened up. So the 9-volt source is no longer going to contribute anything. Excuse me. Here is our 2 ohm resistor through which a current IA at 0 plus flows. Here is our voltage, 3IA, 0 plus. Here's our 7 ohm resistor. Our capacitor is going to look like a short circuit because we are replacing it with a 0 volt voltage source, which is the same thing as a short circuit. And our inductor is going to look like a negative 9/14 amp current source having the same direction as the quantity IL. And we need to solve for this quantity IC at 0 plus. So how can we solve for IC? This is not meant to be a trick question. We could, but mesh is unnecessary here. It'll be positive 9/14.
Yeah.
Okay. So this 9/14 or negative 9/14 amp of current is going to come around this bottom right-hand corner, and it's going to see this node that IC at 0 plus is pointed into. So it has an option here. It can go through the short circuit, or it can go through this path, which we know has an equivalent resistance of 6 ohms. It's obviously going to choose the short circuit, but it's flowing up through the short circuit, which is why IC at 0 plus has to be negative 9/14 or positive 9/14 of an amp. Bradley.
Will IA not affect it?
So IA will not affect anything here. IA is defined as the current flowing through the 2 ohm resistor, which is down, which is 0. So this just looks like a short circuit. So IC of 0 plus is equal to positive 9/14 of an amp. Are we okay with that analysis? Anything seem wild or crazy? All right. Do we need to analyze this circuit at t is equal to infinity? Let's look back at our original circuit. There is no source, no independent source left in after our switch opens up, which means we do not need to analyze the circuit at t is equal to infinity, because all of the energy stored here is just going to get transferred to this equivalent resistance, right? So we can say definitively, all of our signals are going to decay to 0. They're not going to settle to some DC value because there is no DC excitation that is occurring. Okay. So no analysis is required for t is equal to infinity. So we are ready to develop our system of equations. Our voltage V of t, which represents the voltage over all of our elements in parallel, but specifically here, our capacitor voltage, is given by A1E to the S1T plus A2E to the S2T. And thus, V at 0 plus is simply A1 plus A2. And from this, we see that A1 plus A2 is equal to 0 volts. There's our first equation. Anybody have any problems with this? All right. Our inductor current, IC of T, is C times the derivative of our voltage expression, or C times S1 A1 e to the S1T plus S2 A2 e to the S2T. And from this guy, we can see that negative 9/14 of an amp is equal to 25 millifarads times, oh, sorry, I jumped ahead here. Let me scratch that out. IC of 0 plus is equal to C S1 A1 plus S2 A2. Here we go. 9/14 of an amp is equal to 25 millifarads times S1 A1 plus S2 A2. And this is my second equation. And what I'm actually going to do here is I'm going to rewrite this as 9/14 of an amp divided by 25 millifarads. The reason why I'm rewriting it like that is because I stored S1 and S2 as variables in my calculator so that I can literally have my first equation, which I can put into my calculator, and my second equation in a form that I can directly put into my calculator so that I can solve these guys fairly trivial. So using my 2x2 system solver, the coefficient for A1 in my first equation is 1. The coefficient for A2 in my first equation is 1, and my constant term is 0. The coefficient for A1 in my second equation is S1, which I stored as variable A. The coefficient for A2 in my second equation is S2, which I stored as variable B. And then my constant term is 9/14 divided by 25 times 10 to the minus 3. Does what have to be negative? It shouldn't be negative because IC at 0 plus was positive. And that's the value that we're plugging in. So when I solve this system, I get A1 is equal to 8.849 volts, and A2 is equal to negative 8.849. So using these numbers, we can say that VC, or excuse me, V of T is equal to 8.849 e to the minus, look back at what S1 was, negative 1.880 T minus 8.849 e to the S2 negative 4.786 T volts. And from this, IA of T is simply V of T over 6 ohms, or 1.475 e to the minus 1.880 t minus 1.475 e to the minus 4.786 t. What we will do now is simulate it and make sure that we're right. I love these because there's a built-in way to check our answer. Doesn't help at all to tell us where the mistake was made if we made one, unfortunately. But if we are diligent about our application of circuit theory in the analysis at t is equal to 0 minus, t is equal to 0 plus, etc., we are going to be good the overwhelming majority of the time. A1 was 8.849 and A2 is the exact same thing but negative. Yes. All right. So no, that's for this very specific system. All right. So let's build our circuit. This was a 9-volt source, if I'm not mistaken. I did not need to put the V. Here's our 2 ohm resistor. As a reminder, LT Spice does not have dependent sources as we call them. They have behavioral sources. So we're going to get that by typing in BV for a behavioral voltage source. Where I'm going to right click down here and change my function to be 3 times the current I that's flowing through resistor R I R1. We are going to have to check to make sure that things are pointing in the right direction here, but I'm saying that this source depends on the current flowing down through this resistor, which is exactly what the current IA is doing in our original circuit diagram. Then I have a 7 ohm resistor over here. Think smaller and move stuff over. This is my capacitor, which was 25 millifarads. And let's put my inductor here, which was 4.444 Henrys. All right, so as I talked about at the end of class, I believe on Friday, I choose to put my negative polarity terminal or my reference terminal, excuse me, at the negative polarity terminal of my capacitor, which is going to be the bottom node in this case. I don't know that I mentioned this on Friday, but I always have been of the practice to give myself a little stub of wire here to attach my ground node to. And the reason why is because sometimes, not often, but sometimes, if you were to connect the ground node to this big long thing here, it gives you a weird result. I could not begin to tell you why, and it is not consistent, but it doesn't do it if you give yourself a little piece of wire. So I just got in the habit of giving myself a little piece of wire. I am going to label this top node as VC. It'll be the positive polarity terminal of my capacitor. And now I'm going to give myself my initial conditions. So dot IC, the voltage at node VC is 0. So that's my initial, the voltage drop across my capacitor at T is equal to 0 was 0 volts, right? Control M to get my second line, dot IC, the current flowing through inductor L1 was negative 9/14. So that's, I have to use my calculator for this, 9/14. 0.64286. And I'll just drop these guys down here. And our simulation, let's start with 10 seconds and see what happens. So 10 seconds might be a little too much. So let's change that to 5. That seems reasonable. All right, so here's the point where we put in our mathematical expression. So that was,
Here's some information.
shut up, watch. 1.475 times EXP negative 1.880 multiplied by time minus 1.475 times EXP S2 was negative 4.786 multiplied by time, and I'll be damned, it matches exactly, which means we did everything correct. I was mildly worried. I didn't remember the 9/14 from doing this previously, but I probably just wrote it out as a decimal. All right, so just to verify some things here real quick, one thing that you do have to pay attention to when you have a dependent source that is dependent on a current is that we have to make sure that the current that we are referencing is actually in the same direction as indicated on the schematic diagram, right? So this current probe tells me that the current IR1 is flowing down through resistor R1, which is the direction that we wanted, right? If for whatever reason, so if I took this resistor out and rotated it twice, it would look identical, but now the current would be flowing up. We would just put a negative sign here to force it to be in the right direction is what we want. That's all we would have to do.
So if you rotate resistors, they change the traction, like outputs and stuff.
Yes, absolutely. Yeah. No, you can rotate away. Just make sure when you do a transient analysis that you mouse over things and make sure that the currents are flowing in the direction that you expect. So for this 7 ohm resistor, we could rotate it all day long and it would make no difference because nothing depends on the current flowing through it. But it's this guy specifically that we have to pay attention to because our dependent or our controlling variable is the current that flows through this resistor direction that specific. Exactly right. Yeah, exactly right. Yeah, LT Spice will take care of the rest, but for this particular resistor, not having the current pointing down messes things up because that's what our dependency is related to. All right. We technically have 25 minutes left of class. Do you want to do something else, or do you want to take that 25 minutes and work on homework stuffs? If everyone else says the class is over, then sure. Are we good for the day? Anybody got anything else they want to talk to me about? Yes, ma'am.
Can you say one more time why we didn't evaluate it?
Sure. So let's look back at our circuit.
I just wanted to write it down.
Okay. So we're only required to analyze the circuit at t is equal to infinity if there are dependent sources left in during the transient condition, right? So this 9-volt source is taken out. It's no longer connected to our circuit. But if the switch had been going the opposite direction, so that the 9-volt source was added in during the transient condition, we would absolutely have to analyze it at infinity. So anytime there is an independent source left in or connected to our energy storage elements, we have to analyze that t is equal to infinity. If there are no independent elements connected to our energy storage elements in any way, shape, or form, we don't need to analyze that t is equal to infinity.
During the transition.
Exactly right. Connor.
For intermediate calculations on the exam, 3 decimal places.
Sure. Or I was going to say fractions, but I kind of hate fractions, so 3 decimal places will be great. Yeah. The reason why I hate fractions is because I have to go and type them out and make sure that you did it right. They're more correct for sure, but 99% of the work that I do, I use decimals. I don't know why I elected not to today for whatever reason, but just feeling squirrely, I guess. Yeah. 3 decimal places is appropriate for me.